A very good evening to our respected lecturers and my fellow friends. Today, we would like to bring upon our video presentation for the course KIB1011 Statics and Mechanics of Materials. So, my name is Po Chong Xuan, and my other group members are Eric Chan Yen Lee, Goh Yen Cheong, and Ka Heng. So, the agenda of our video presentation today is firstly, introduction to our assignment, secondly, calculation, thirdly, discussions, and lastly, conclusions. So, now let's have a look at our introduction and objectives. So, our overall project objective is for the course KIB1011 Statics and Mechanics of Materials. So, in the process of preparing our report, we are required to find, observe, and analyze real-life examples of biomedical devices. In our case study, the biomedical device that we have chosen is the axillary crutch. So, we will analyze the axillary crutch in terms of statics and mechanics. So, what are crutches? Crutches are a type of walking aid that serve to increase the size of an individual's base of support. So, they transfer weight from the legs to the upper body and are often used by people who cannot use their legs to support their weight. For example, someone who suffers from short-term injuries to lifelong disabilities. So, here are some examples of crutches. The first one is the axillary crutch, which we'll be analyzing in our video assignment and also our project. And then there's the elbow crutch and the gutter crutch. There are many more types of crutches. So, now let's have a look about statics. So, statics is basically the branch of mechanics that focuses on the equilibrium of objects at rest, meaning that they are not in motion. So, the key concept of statics is the analysis of forces acting on objects without considering their motion. So, the primary goal is to determine the conditions under which an object remains stationary. Thus, our calculations in our assignment will be made by assuming that the object or member that we are analyzing is under static equilibrium conditions, where there are no movements of the subject, object, or member in the instantaneous position by external forces. And there is a net result of 0 in all directions for all the applied loads and reactions. So, what aspects will we analyze in our assignment? So, the first learning objective of our assignment is forces on the axillary crutch. Secondly, we will analyze axial, bending, and torsional loads. Thirdly, we will analyze moment and inertia based analysis. And fourth, we will analyze stress and deformation on the member. And lastly, we are required to perform effectively as a team in analyzing. That's all.
Here I will introduce to you guys how and what formula we use to analyze in these calculations. Okay, so I'm Eric Chan Yen Lee. My lecture number is 22003227, and I'll be in charge in 2 cases. Okay? So the first cases is we're gonna analyze what are the component force exerted on the crutches, the axillary crutches. Okay? So as you guys can see, there's the free body diagram here, the free body diagrams, and you can see the F1, F2 is the normal force exerted by the patients on the crutches. Okay? So F1 is denoted as the normal force exerted on the first crutches, and F2 is denoted as the second crutches. So you can see the patient is not holding the crutches vertically straight up, which he is holding the crutches in the correct way here, which is there's an angle subjected between his body and the body of the crutches, which is 22, which we assume here is a 22 degrees Celsius. Okay, so first we're gonna prove F2 equal to F1, so we use the equilibrium analysis. The sum of the x component, the horizontal component of force, is equal to 0. So here we find the resultant component is F2 and F1, right? So we find the horizontal component of each F1 and F2, so we equal them, so we get F2 equal to F1. We cancel out the sine 22 here, so we get F2 equal to F1. And then next, we use the same logic, same theory here. We use the equilibrium analysis, which the sum of the vertical components is equal to 0. So there's three vertical force. If we look into this free body diagram, we can see there's a vertical components of F1 and F2, and the mg, which is the weight of the patients. So we equal them up together. We get F1 equal to 338.57 Newton, and then which is somehow equal to F2. Okay. Right, so next. So okay, now we look at the free body diagrams. At the particular parts, which is at the tip of the crutch. Yeah, here we assume the crutch is not in movement, so there's a static friction force acted at the tip of the crutch. So we use the equilibrium analysis of horizontal components, which is the sum of Fx equal to 0. So there's 2 horizontal components here, which is the static friction force and the horizontal component of F2. Okay, so we equal them up together, and then we do a bit calculation, and then we get the static friction force is equal to 136.583 Newton. And next, we use the same theory, which is the equilibrium analysis of vertical force. Okay, so same here, there's 2 vertical force, which is the first is the normal force acted at the tip here, at the tip of the crutch, which I denoted as n tip here. And then the second is the vertical component of F2. Okay, here I denoted as F2y, which is a y component of F2. Okay, so we equal them up together, and we get the n tip is equal to 313.92 Newton. Okay, since we get the value of Fs, which is the static friction force, and the n, which is the normal force, right? Then we can calculate into this calculation, and then we can compute out the value of mu s. Mu s is the static friction coefficient. So the static friction coefficient is 2.475. So the static friction coefficient is determined by the material of an object. So the material, we know, logically speaking, the material that met up at the tip of the crutch is rubber, right? So we can compute that the static friction coefficient of rubber is within this range, which is 2.475. Right, next, now we look at case 2. So in case 2, we're gonna analyze 3 aspects of forces here. So the first one is the action of axial. The second is action of bendings, which is the force that causes the bending of the crutches, and the third is the torsional loads that exert on the crutches. For action of axial, we aim to find the normal stress that is exerted on the hand grip board of the crutches. Since we assume the weight of the patient is exerted directly in between the upright, the left uprights and the right uprights. The uprights is the second portions that we have to look into in this case, okay, which is the body tube here. The body tube, there's a specific name for this body tube, which is the uprights. Okay, so there's left uprights and right uprights. So since the weight of the patient is exerted directly between the uprights, right, of the axillary crutches, then we can conclude that the weight exerted is directly perpendicular to the handleboard. And then we know the force is evenly distributed to both ends of the handle of boards, okay, which is the left uprights and right uprights, which I denoted as our upright ones is equal to our upright 2. Okay, the R here is the uprights. Okay, then the normal force that exerted on both uprights is just the weight of the patient divided by 2, because it is evenly distributed in both uprights. So we get the normal force exerted in each upright is equal to 169.285 Newton. Okay, next. So yeah, next, in order to find the normal stress exerted on the upright, first we have to measure the radius of the upright's outer radius. So we divide the outer diameter by 2, so we get the outer radius, and then same goes with the inner radius. We divide the inner diameter by 2, so we get the inner radius. So we have to find the area, so we just use the radius, the outer radius, the formula of area, which is pi r squared. So we use the outer radius minus the area with the inner radius. Okay, so we get the area of the upright, the cross section area of uprights is equal to 0.321 cm squared. So same goes with AC2, because the important parameters of area, which is the radius of upright 1 is equal to upright 2. So we can conclude that the area calculated at the end of calculation is equal to AC2. Okay, next. Okay, yeah, since we successfully get the two important parameters, which is the force, the normal force exerted on the uprights and the cross-section area of the uprights, so we can compute the normal stress that acted upon on each upright. So we use the formula sigma equal to F over A. Okay, so we start the value that we calculated just now, and then we get the normal stress on upright 1 is 5.2737 times 10 to the power negative 6 Newton meter squared. Okay, so since the parameter is same in upright 1 is same as upright 2, so we can conclude that the normal stress is also same as the upright 2. Right, next. Okay, so this is the second goal we're gonna analyze in case 2, which is the maximum shearing stress exerted on the hand grip board. Okay, which is, yeah, this is the reason we have to find the force that caused the torsional loads. Okay, the torsional loads. Right, so so once the patient is walking on the crutches, right, and then he actually apply the top on the hand grip board. Okay, so here we assume the hand grip at the top applied by the patient is equal to 100 Newton. Okay, 100 Newton, and then we want to maintain the hand grip board in equilibrium positions, in static equilibrium positions. So there's axis, the internal top. So here I denoted as TA and TB. TA is the internal top at NA, and TB is internal top at NB. So we use the equilibrium analysis of moments. We sum the moment together, then we get the TA plus TB is actually equal to 100 Newton. Okay, once we get the TA and TB, but we want to find only one unknowns. Okay, for our better calculation, just later on. So we use the formula of angle of twisting. Okay, so the phi A plus phi B is equal to 0. Then we get the TA is the internal top at NA, and LAC is the length between A and C. C is the locations where the applied top is located. And then over GA and JA. G is the modular of rigidity, and J is the polar moment of inertia. Okay, since the diameter and the material used at both ends of hand grip both are the same, so hence we can assume that the modulus of rigidity G and the polar moment of inertia J at the end of A and B are actually the same. So we know GA is equal to GB and JA is equal to JB. And next, since we also assume the applied torque is assumed to be exerted at the center of hand grip, which is right in the middle of the hand grip board, so we know that the LAC is also equal to LBC. Now we can equate the expressions, then we get TA equal to TB. Okay. Next, okay, here comes to our end of the calculations. Okay, since we get all the data that we want to use to calculate the tau max, which is the maximum shearing stress exerted on the hand grip board. Okay, so yeah, we have to find the polar moment of inertia first. Then the C4 is the radius of the hand grip board. Okay, so the radius of hand grip board is this is a solid board, so there's not a hollow board. There's not a hollow tube. This is a solid board. So we just use the formula, the radius to the power 4, and then times pi divided by 2. So we get the polar moment of inertia at the board here, hand grip board here is 8.8536 times 10 to the power negative 11. So we sub the J here into the elastic torsion formula. Then we sub the T. T is the 50, which we have calculated just now. And then C is the radius of the board. So we get the maximum sharing stress accidental on board is 1.525 gigapascal. So here is so that's all for me, and I will pass the stage to Kai to proceed on the calculation part 2. Right, thank you.
Good evening, Dr. Chan. My name is Heng, entry number 23005037. Today I would like to, for my part, I will talk about the pure bending. Okay, pure bending. In pure bending, the pre-matic members are subjected to equal and opposite couple acting in the same longitudinal plane as shown in the figure below. So we can see the moment here, the M prime is actually the magnitude is equal to the moment, enters, okay, this but in opposite direction. Okay, so we can using this concept to find the maximum tensile and also the compressive stress, also known as the maximum normal stress due to bending, with this formula. Negative M is moment, Y is the distance, alright, distance, later we'll discuss about that, and then I is equal to the moment of inertia. So to find the resulting couple moment, okay, which is the M and N prime, we just need to find one, and then the another one will be equal magnitude, because it is a couple moment. So we first find the distance between the support D, and now the support D here is given by, okay, 129.7, which is here. You can see this is the one that using the inner, we want to find the inner distance between the both up, right? So, and then we minus, okay, by 2, okay, by 2 multiply, because we got 2, alright, we got 2, okay, we minus by this one. Okay, we minus this this thing. Okay, to this 2 distance. So here is 1 is 20.92. So we multiply minus 2. Okay, because we just need the middle one, the middle part here, Okay, so we minus it by 20.92, and then we can get 87.86 mm. So we can find the moment after this, which is using the formula, which is Ft. Alright, the force multiplied by distance, which is the force given. Okay, we're using the force upwards. Using the force upward that is calculated here. Alright, which is the we can using the formula calculated here, 338.57 Newton. Then we divide it. Okay, then we divide it by the we multiply by the distance, we can get 14.87 Newton meter. Alright, so this is the M, the couple moment, same magnitude, opposite directions. Okay, so to determine the Y, what is the distance between the neutral axis and also the particular point in the member. So we first need to find the centroid of the member first, and then because this cross section actually is circular, so the centroid is actually directly at the center. So we just need to using the diameter divided by 2, which is another word is the radius of the member. Okay, so we can calculate it by using this length, this is the diameter, and we just need the half. Okay, so we're using 5.4 mm divided by 2, which is we can get the meter, like if we change to meter, then it's get 2.74 multiply 10 to the power of -3 meter. So then we can determine the moment of inertia, okay, of the member, alright, which is using the formula, this formula to calculate the circular. Okay, if we want to calculate the moment of inertia of the circle, so we using this formula, substitute in the R value, okay, then we can get this, okay, 4.43 multiply 10 to the power of -11, okay, meter to the power of 4 and then we can calculate it by inserting all the value that calculate above into this formula, okay, which is the maximum compressive stress is negative 919.72 megapascal, and the maximum tensile strength is actually 919.72 megapascal. So that's the maximum tensile strength. Okay, the maximum tensile stress. Okay, we can conclude that actually, okay, the maximum compressive stress occur at the upper part of the circular cross section, and the maximum tensile stress occur at the lower part of the circular cross section. Okay, so we can conclude that, okay, it's actually the same, but just in the opposite. Okay, you can see that the value is actually the same, 919.72. Okay, so and then we can calculate. Okay, we can using the formula. Okay, to calculate. Okay, we can also using this formula. Okay, to calculate the maximum tensile and compressive stress. But if using this formula, we can try it. Okay, by using the S is equal to the pi over 32 dq. So we can using this formula to sub in the formula value in, just sub in value in S, and then we get the M, which is this calculated above at the moment. So we can get actually the same value. Of course, it's a slight difference lah. Okay, as we rounded off some of the value. Okay, just okay, a little bit difference. Okay, and then the deformation due to the bending moment, alright, is actually quantified by the curvature. Okay, we're using the formula. Actually, this is the radius of curvature. Okay, this radius of curvature, represented by radius of curvature, and then this is M over EI, which is okay. We can see this okay, M over EI. E is the modulus, okay, value, and then the I is the moment of inertia. M is the moment. So we can just writing the value, we can calculate the radius of curvature, which is 0.5958 meter. Okay, so in this case we can see that. Okay, and then the moment of inertia in this case, of course, is the same lah. Okay, moment of inertia just now, okay, above. So this is actually dragging above, okay, the value above 1, and then we go drag it down only. So the moment of inertia. And then now we go to the stress and deformation. Actually very easy, this one. Stress and deformation. Okay, we're just using the weight of the patient. Okay, in this case we assume that the weight is 64 kg of the patient, and then we multiply by the gravity, so we can get 627.84 Newton. And then the force exerted by the patient on each crush, we're just using the weight, okay, the force, the weight of the patient, multiplied by 1 over the 2 cos 22, the cosine, and then we can equal to the formula 338.57 Newton each crush. Okay, so area of the cross section of the hand grip board is equal to the 5.48 multiplied 10 to the power of -3. This one is the diameter just now. Okay, the diameter. Okay, that we mentioned just now. This one is diameter. Okay, so the R growth, of course, we divided by 2 only to find the radius, and then we substitute in the value, which is the area pi r square, shear stress on the hand grip both of the crutch. Okay, and then the shear stress we can calculate by using the force mentioned just now on each crutch divided by the area. We can get the value, and the shear strength using the formula, okay, which is the fixed value of the stress. Okay, the modulus here, and then we divide by 2 is 1.65 multiplied 10 to the power of 8. Since the shear strength greater than the shear stress, the value here, you can see the value is greater, obviously. 1 is 10 to the power of 8, 1 is 10 to the power of 7. So it is strong enough to bear the patient's weight. So that is my part for for the pure bending calculation and also the stress and deformation calculation. Thank you.
Hi, my name is Chong and the lecture number is 23064570. Now I'm going to present the discussion part of our assignment. So our discussion can divide into two parts, which is the problem and aspects that may cause failure, and the second part is the solution. So the factors that may cause failure of the axillary crush includes the overloading, bending, heaviness, and also corrosion. And the solution that we figure out includes the clear weight limit information, professional consultation, confirmed structural analysis, anodizing, and also regular cleaning. So the factor 1, overloading, is the predominant cause of axillary crush failure, commonly stemming from patient being overweight and exerting weight beyond the maximum stress limit. When this limit is surpassed, the axillary crush undergoes elastic formation, and if the stress exceeds the elastic region, it transitions into irreversible plastic deformation. In such cases, the component of the axillary crush may eventually fail under the sustained stress. So the solution for overloading is the manufacturer can significantly address the overloading issue in axillary crutches by providing clear weight limit information. This involves incorporating stickers or labels on the crutches specifying the maximum allowable weight for patients. Simultaneously, healthcare professionals such as doctors and nurses play a crucial role in overseeing the proper use of axillary crutches. They should ensure patients use crutches with suitable weight limits, conducting a thorough process of measuring the patient's weight and guiding them on correct usage. In cases where the axillary crutch is not suitable, alternative crutches like elbow or gutter crutches are recommended, with accompanying warning about the consequence of overloading to prevent worsening patient's conditions. Additionally, emphasizing professional consultation is pivotal in mitigating the overloading issue. Patients are advised against carrying heavy objects while using the crutch. Recognizing that the combined weight of patient and objects may lead to overloading, seeking expert guidance is crucial, and patients are encouraged to consult with physical therapists or medical professionals for proper selection and usage of axillary crutches. This professional input ensures not only optimal safety but also functionality, providing patients with tailored advice for their specific needs. So the factor 2, bending, also known as flexor. This phenomenon occurs when a slender structural element is subjected to an external load, perpendicular to its longitudinal axis. In the case of pure bending, the member uniformly bends, forming a circular arc and experiencing both tensile and compressive stress. However, when the applied load surpasses the maximum stress limits, plastic deformation enters a process characterized by irreversible changes in size or shape. This plastic deformation diminishes the strength and durability of the crutch, ultimately leading to failure. So the third factor, which is the heaviness, is also a significant problem that contributing to the failure of the axillary crutch. The stainless steel composition of the analyzed axillary crutch model was thoroughly burdensome for routine daily use by patients. The heightened weight places an additional load on patient's arm, causing discomfort during usage. This weight-related challenge underscores the need for material shift to alleviate the burden on patients and enhance the overall usability of axillary crutches. In addressing the bending problem of the axillary crutch model under analysis, it is constructed from stainless steel with a modulus of elasticity measuring 200 MPa, deemed sufficient to support patients within both normal and heavily weighted ranges. However, to counter the weight-related issue, we propose an alternative solution by recommending the use of aluminium in manufacturing the crutches. This suggestion is grounded in the favorable characteristic of aluminium, which boasts a lower density of 2,710 kg per meter cube compared to stainless steel's 7,930 kg per meter cube, rendering aluminium approximately 1/3 of the weight of stainless steel. Moreover, aluminium exhibits a modulus of elasticity of 68 GPa, surpassing that of stainless steel. The collective outcome underscores that aluminium, being lighter and possessing superior resistance to bending with a high maximum tensile and compressive stress limit, stands as a viable material choice for addressing the weight-related concerns associated. So this is the table for the material and the density. It includes the aluminium, stainless steel, and also the titanium. And the following factor is the corrosion. Corrosion poses a significant challenge for axillary crutch, commonly carved from aluminium or stainless steel. Although these materials are widely used, they are not entirely resistant to corrosion. The susceptibility of stainless steel depends on its chromium content, with higher level reducing the likelihood of rust. On the other hand, while aluminium does not rust, it can corrode over time. The protective aluminium oxide coating renews itself, but exposure to harsh conditions can stabilize it. In both cases, prolonged exposure to damaging elements like chemicals, saline, grease, moisture, or heat leads to corrosion, compromising the crutch's strength and reducing overall durability. Addressing this corrosion issue is vital to ensure the longevity and performance of the crutches. To effectively address the corrosion issue in axillary crutches, implementing the anodizing process proved instrumental for both aluminium and stainless steel variants. Anodizing an electrochemical process creates a protective oxide layer on aluminium surface, significantly boosting corrosion resistance and providing a durable finish to the crutches. Additionally, regular cleaning practices play a vital role in corrosion prevention. Removing accumulated dirt, salt, or pollutants using mud, soapy water, and a softy brush helps maintain the integrity of the crutch surface. It's imperative to avoid aggressive cleaners or harsh chemicals that could potentially damage the protective oxide layer of aluminium. Opting for non-aggressive cleaners suitable for both aluminium and stainless steel surfaces ensure effective corrosion prevention. So come to our conclusion. In our group assignment, we focus on analyzing axillary crutches, examining their components and force at play. Design issues were identified, and we present detailed explanation along with solution for improvement. Our learning objectives were successfully achieved by constructing 3 bone diagrams applying equilibrium-based and static rigid body assumption, and conducting moment-based analysis. We calculated stress, deformation, and affirmed the generally strength of axillary crutches under a 64 kg load. Identified areas for improvement were addressed with suggestions for enhanced design and performance. Looking ahead, we acknowledge potential stability challenge under increased forces, expressing optimism for future advancement through the ongoing research in statics and mechanics, leading to improved design and increased suitability for diverse patient needs. So here are some references that we use in completing our assignment. And that's all from us. Thank you.